Okay, so we wanted to just confirm that we understood everything and fill in the experimental validation at shorter wavelengths. And so this was the predictions, and this was our initial measurements. But then we have slightly more intense lasers in the short wavelength region of the spectrum, and so we started to turn up the intensity, and then we got this surprise, which we're calling the ultraviolet surprise, which is different from the usual one. We suddenly saw harmonics that were as bright as if you used the long wavelength driving lasers, but they came out as discrete peaks, like they normally come. And, you know, we all know how to do Fourier transforms, all right? So if your harmonics come out as a single burst, what in time, so an isolated burst in time, what kind of spectrum must that correspond to? And what kind of Gaussian? Yeah, it's a continuum, all right? Because to be able to make an isolated burst, you need a fairly broad continuum. And that's what this does. So this phase matching window, and we've confirmed this experimentally, for long driving laser wavelengths, the phase matching window is less than a half an optical cycle. But you look at this, and you can immediately say, without any, you don't even need to do any quantum calculations or anything, but if you've got a periodic spectrum, got a cone, then your phase matching window, does it span one cycle or multiple cycles? Yeah, it has to. This is just Fourier transform. We don't need to use any physics. So this had us scratching our heads. What is going on? How can phase matching suddenly occur over multiple cycles? We understood things, like I explained, that on the leading edge of the pulse, the laser was going too slow. On the trailing edge, the laser was going too fast. But suddenly, how does the laser seem to go at the right speed for multiple cycles of the driving laser? And of course, we scratched our head, we looked back. I mean, why wasn't this seen before? Because actually, the first harmonics were done, because the first femtosecond lasers were often, the first powerful femtosecond lasers were based on exomers. Those could pack they had a lot of energy. So we went back to see, well, why are we seeing this and why wasn't it seen before? And in fact, there's some beautiful work that showed that if you used a 248 nanometer krypton fluoride exomer laser, they had a lot of energy, maybe 100 navijoules or something. They had 400 femtosecond pulses, and you could see they saw harmonics down to 5 nanometers. But they were very low efficiency, 10 to the minus 12. So not phase matched. But we were seeing them bright as a well phase matched beam. So, in fact, this is the experimental data, and you can see you expect very bright harmonics for ultraviolet lasers in the vacuum ultraviolet region. The cycle time is much shorter if you've got a short wavelength laser driver, so there's less quantum diffusion. So it's this really bright single atom emission, and you expect that. But what we didn't expect was this plateau that went all the way out to 300 eV, and that optimizes at very high pressures, 400 torr. And our colleagues in Salamanca, Luis Blas group, did this calculation where, because tunnel ionization still, and strong ionization, still applies, and it's very appropriate for UV driving lasers, and so they calculated what ionization stages must be present for us to be seeing emission from argon. It turned out this was from argon in this region of the spectrum, and these emissions had to be coming from multiply ionized ions. Now, monoxide ions had been seen before, but what had not been seen before was bright emission from ions, and and so then that got us thinking, so what is different about refractive indices in the ultraviolet region of the spectrum? Do they get bigger or smaller for light as you go from the visible to the ultraviolet, you will learn in undergrad that the refractive index goes, does it go up or down? It goes up, yeah. And it goes up because, of course, you're approaching all the resonances in the ultraviolet. Now, you think...
You don't get sunburn if you're sitting in the car.
Exactly.
The glass.
Exactly. So they go up, yes, exactly. And they get, yeah, absorbed, yeah. So if the refractive indices goes up for the laser, does that make it easier to slow the laser down or harder? I know I'm asking a lot, first lecture in the morning. So what is the phase velocity of light is given by the speed of light in vacuum divided by the refractive index, all right, C over N. And so if N goes up, the phase velocity will tend to slow down. So it turns out in the ultraviolet, for ultraviolet driving lasers, because the refractive indices of the atoms, and not only atoms but ions, because you can't neglect, in the mid-infrared, the refractive index of an ion is very low, but if you calculate the refractive index of an ion in the ultraviolet, it's still quite significant. So you get help in phase matching. So what happens is, as you go from the infrared through the visible through the ultraviolet, the linear refractive indices of atoms and ions increase, but any influence of a plasma decreases. And so it becomes easier to force the laser to travel at the speed of light in vacuum. So phase matching becomes easier. And so, that has you win in two ways, because your quantum diffusion is less, because your cycle time is less, so the electron spends less time in the continuum. So if you look at the quantum diffusion, there's less transverse quantum diffusion. You have to give it the same energy.
Margaret?
Yes.
What is the fractional ionization typically?
It's
very high.
So if you drive with high sapphire lasers or with mid-infrared lasers, if you want to phase match, then the fractional ionization is less than 10%, and sometimes less than 1%. But for ultraviolet lasers, you can go up to 4 or 5 times ionized and still phase match. And that is just weird. I mean, because again, coming from a plasma physics perspective, in a 5 times ionized plasma, we would say nothing is possible. There's strong plasma gradients everywhere, and so the fact that harmonics will phase match it under these circumstances are actually quite surprising to us. And so what we've plotted here, it's a bit complicated, but it shows this phase matching window in yellow for the normal way one would do harmonic generation for Ti sapphire compared to these UV driving lasers. So you can see for Ti sapphire you get, depending on you can modify the conditions a little bit, but it's a couple of cycles, 2 or 3 cycles. You can make it go up to 10 if you want. But for the ultraviolet driving lasers, the phase matching window is much broader. It spans multiple cycles, which we know it must, because you get these very narrow peaks. So, but it was nice that that actually an analysis could show that. How am I doing? I'm doing okay time-wise, am I? Or
Yeah.
Okay, good. So then, Tony, we don't know the limit in either direction. So it's very interesting what will be the best route. And then what happens as you approach ionization potential. So there's a lot of really interesting physics questions here that would be great to shed some light on.
I'm still a little bit puzzled. As you go to longer driving wavelengths, the phase matching property for the driving laser gets better.
Yes.
But you're producing many higher orders of
Correct. It's a much higher order process. Correct.
And so the index of refraction problems you get.
And delta K, and the phase slip is, delta K is always, K times the fundamental minus delta K, and so your phase matching in some ways you would expect it not to work because your order is going up so high, and it does. because of, again, strong field ionization. It all comes back to, because, you know, it's, and the harmonic scaling, it's I lambda squared. So as the wavelength goes up, your intensity goes down. And in the infrared, tunnel ionization is favored. That right, because your field, you're depressing that barrier for an eon by the time you're when you're at 4 micron driving laser, your cycle is 13 femtoseconds. So you pull that poor atom and kind of held it there, essentially for many femtoseconds. Right? But it's amazing to me that the synchronization is still perfect. You know, there is no any kind of decoherence at all. But I guess it's just because in the infrared, you know, it is always tunnel ionization will always win versus multiphoton. So many physics questions that can be addressed as you know, we'd love to see some more theory that explores for these limits, because you know, things we thought would be an issue like you know, the Lorentz force. You can take care of those with other applied light fields. So, you know, they're, to our knowledge, and of course this is famous last words as an experimentalist, we don't know where the limit is, but that just is we don't know where the limit is. Yeah. And so then, maybe I'll talk about circularly polarized harmonics and phase matching in those fields. The ideas have been around for quite a long time. Work from Wilhelm Becker's group in Germany and his collaborators. And so, so let's see how we think about it. So, and this is work we did in collaboration with Oren Cohen's group at Technion. And so this is the fields of two counter-rotating circularly polarized drivers. And if you look at, so what do these two light fields combine to? And depending on the relative intensity of these two light fields, you'll always get something that's threefold symmetric for these, for the fundamental and second harmonic of Pi-Sapphire. And if you do the right ratio, you'll actually get this clover leaf that's not special. In fact, clover leaf is not the one you want, but it's still a threefold symmetric thing that has lobes, 3 lobes like this. And where would the electron ionize in this field? Would it ionize here, or here, or here? Where would the electron tend to ionize? At the peak of the field, right? So it ionizes 3 times the cycle and then returns, and that's what we were trying to convey here. They come out here, here, and here, and then fraction of a cycle later, the electron returns and you get the X-ray burst. And this is how you can think about how you get these circularly polarized photons out. Each harmonic photon has to be the combination of the different circularly polarized photons you're irradiating the atom with, but because it can only take away 1 unit of photon spin angular momentum, you can only grab 1 more red than blue. You can grab 1 more blue than red or 1 more red than blue, but you can't, that is the only combination that's allowed, because otherwise it doesn't conserve photon spin angular momentum. So you have to get out either a right or a left circularly polarized harmonic. And so that's essentially saying this, that to conserve energy, I just add the number of blue and red photons, and to conserve angular momentum, I can only have 1 more or less of the 2 fields. And this has been known for quite a long time. So what was not known is how you think about phase matching. And normally, if you do 2 color linearly polarized laser fields to make harmonics, will red and blue light travel in any medium at the same speed? Do you want to hazard a guess? Yes or no? Do you think?
No.
No, exactly. And the reason why is that there's some phase slip as they propagate. And while you could, and so the intensity will modulate, and you can do a quasi-phase matching based on this, but in general, you won't do perfect phase matching. But think about these circularly polarized fields. If there's a phase slip between the red and blue, which will happen as those fields are traveling through the medium, all that will happen is your combined field rotates. And now your max intensity is not changing as you're going to the medium, it's just rotating slowly. So phase matching works even though you're using multiple colors. It's still perfect. So you can do as well as linear. So that's how you get the bright beams. I won't bother with the math, but this is fun if you're bored, and it is fun to do these calculations to work out the conservation of energy and photon spin angular momentum, and it's a lot of fun if you use non-commensurate colors. So we did that recently just to see if we could do this in the soft X-ray region, and I'll finish up in a few graphs here. So instead of doing 800 nanometers and the frequency double 400 nanometers, used 800 nanometers and 1.3 microns, the mid-infrared, which is the same approach you use to make linearly polarized soft X-rays. But now they're non-commensurate, so it takes a little bit of, you can work it all out, and then what you find after much ado, we drove ourselves crazy, all the theorists and experimentalists, trying to figure out what the selection was and what's happening. But essentially, for these pair, you get a beautiful 8 bursts in 13 femtoseconds. This, so our 13 femtoseconds is the common multiple of the two colors, and so 8 times. You know, the electron, of course, just like Lars was talking about yesterday, you know, the electron is born far, you know, born in, away from the ion because it's born at some position where it tunnels, and so it's born here. And then for the right intensity ratio, it will take a trajectory. The ones that give the harmonics are the ones that go almost linear and then return. And they're doing that 8 times per cycle. Not per cycle, 8 times per 13 femtosecond, which is just the repeat time of the fields. And phase matching works there too, because if they're phase locked, you get a 3-fold symmetry driving field that doesn't rotate. If there's a phase slip, it rotates, but doesn't matter. And if they're non-commensurate, it does something strange, but it's still not, essentially it's just rotating. And so phase matching works there too. So you get this, again, the beautiful pairs I already showed you in the EUV, that they go up now to about 150 EV, which is nice because this matters for, there's interesting magnetic materials in this, with edges in this routing spectrum, gadolinium, which is very interesting scientifically. And we took a look at this and saw, well, what is this? Why is our circular polarization not perfect? In the EUV, you get these beautiful pairs. You know, the conservation of photon spin angular momentum kills all the harmonics in between, so you get a left circularly polarized harmonic, a right circularly polarized harmonic, and a missing harmonic. Here, because we're using uncommensurate lasers, they're grouped differently. The difference is just the difference in these wavelengths, and the sum is just and here's, one is the sum, one is the difference. We were wondering what this continuum was, but we got these hints because these peaks are coming where you don't expect them to be from conservation of photon spin angular momentum. But then what we realized, what they must be due to are imperfect wave plates. Yeah.
Why are you calling these non-commensurate? The
Oh, fine.
ratio of
So
energies.
that's, yeah, you're right. Yeah, just a slip,
Okay.
a wording slip. Yeah.
Okay.
We went through lots of ways we were talking about this.
Okay.
So, but then we realized, you know, it's hard to get good optics in the mid-infrared, and all that was happening was that our ellipticity was not quite perfect, and the way our terminology, we started talking about buckets. So we said, well, you got this, because you know you can only take one more photon from one bucket than the other, and then what happens if you've got an imperfect wave plate? Because as you're going into the mid-IR, you've taken more and more photons, and so you could grab a wrong polarized photon. In fact, it's more likely as you go into the mid-IR. But in other words, this is just to show it explains beautifully a tiny amount of ellipticity in your driving lasers will give you this underlying continuum. For a while we thought, you see, it was phase matching, and there was some, because you could imagine cases where, especially in your cutoff, your phase matching window will be narrow and then you don't get 3 bursts, and you might get a continuum, but that's not it.
I have trouble because I'm red, green, colorblind.
Oh.
I just want to understand, these pairs,
Yes,
what distinguishes them? It's not
the
their-
circular polarization.
One is right,
One is
one is
right,
left.
and one is left, exactly. And that's just because one corresponds to taking one more red photon than blue photon, and the other one more blue than red. So they're separated by the difference, and also the sum. And the reason this was important was that we don't need perfect optics, because if we know what the ellipticity is, we can work out any magnetic material asymmetry if you know what your ellipticity is. And we can just get gorgeous agreements with more sophisticated models also by just knowing what this shape of the spectrum looks like. It tells you immediately what the ellipticity is, and so you can apply it to any current molecule or material. And we actually did that just to prove to ourselves we kind of, that everything was good. We just measured the magneto-optic absorption coefficient of iron, compared it with synchrotron data, that's in the EUV, and then gadolinium, that's at 150 eV, and also compared it with synchrotron data. It just shows that we can actually, we understand the polarization state of the light. And I think in perhaps I should finish in 5 minutes, is that okay? To just show you in work with the School of Mines and Louis class in Salamanca, we extended the beautiful work Paul's group and others did with crossed beams, but now if you use crossed circularly, oppositely polarized circular beams, you then send all of the right circular polarization harmonics in one direction and the left circular polarized harmonics in the other direction, which is kind of cute. And this just shows you the zero order if you cross. And so if you do it right, you can actually separate them spatially. Each harmonic comes out at a different angle. And you can sort of see that from this, again, just a photon picture. This is your EUV, the left and right circular. If you want to get the next order, you've got to add 4 of these and 3 of these. And so that'll automatically make every harmonic comes out at a different divergence angle. For another, maybe what I wait to one of the later talks this afternoon or tomorrow and talk about how do we measure these light fields, because we are used to the linearly polarized light fields and how to measure them, but with the circularly polarized light fields, the direction of your electric field is changing, and so this is, theory what it should look like for one of these circularly polarized harmonics. This is just the 2 projections, and of course there's a phase difference between the 2 of them. And then the question is, how do you measure this light field? And so maybe with that, I think I'll end just because of the time. Thank you.
Thank you very much, Margaret. Let's see if students come first. Any student before he steals the show, here in the back.
So you talk about this closed shape,
Yes.
and it rotates, I think.
Yes. Yeah.
And you see the harmonic generator at the peak of the pulse.
Yes.
So you have different polarization. And do they still phase match?
They do, because remember, for each one of those harmonics has to take one more or less red or blue photon. So the selection rules are still very stringent. So they still phase match. The rotation is very slow, much slower than, so the rotation is slow enough. So
Tony.
that's fortunate.
For your last slide was right and left circularly polarized. Well, I don't think you have to show it.
Okay.
What is the temporal duration of these harmonics that are right, left circular?
So essentially, for the most part, especially with the combs, when you're looking at the combs, you can sort of back of the envelope even just do a Fourier transform and because they're not very chirped because they get more chirped as you go to very long driving wavelengths, but they're not too chirped at all for these colors. So you know immediately you can take a look at this and say these are phase matched over multiple cycles. And so
Are these hundreds of attoseconds, or are they few femtoseconds? I mean,
essentially that's the theory. Yes, a good question. Yes. So let me show you exactly the calculation here. I may not have the perfect one, but this is a good one. Yes. So this is for the cross beam case. For the cross beam case, that's not what I want to say. Okay. Maybe I. This is the collinear case. So yeah, this is the actual theory prediction, and if we can see the so you can see here. So each burst is 200 seconds. Yeah, which is very much like what linear polarized EUV harmonics when you're not using some kind of gating.
Seconds, roughly.
Yes, that's right. And with the collinear case, because you need, trifoil, because if you restrict the phase matching to one cycle by using some polarization gate or other, then you would get linear, because each burst is linear. And it's just they add together and they phase correctly to give circular. But with the cross beam case, you can actually make an isolated attosecond circuit polarized burst, but not with the collinear. So that's why with the cross beam, with the collinear, you get very nice narrow peaks.
Yeah.
I have a question about the HSG from the different charge states.
Uh-huh.
So the calculations, was that done for each charge state, or like for the system? Like, do you have to include like a volume
Yes.
averaging type?
Exactly.
calculation?
So it was done as sort of analytic. So if we had our theory collaborators calculate what, where the charge states lived, and then built those into a code that with another code from Livermore and Bob Levis group at Temple that estimated, it's not quite right, but can estimate the linear and nonlinear contributions of the different ions. So we could do, this is still the theory on this. I mean, we know it's roughly, it's correct. We get the right 10 femtosecond or 30 femtoseconds. I forget what, a 10 femtosecond temporal window, I'm pretty certain, which in the UV is many, many cycles. Because it's, it's 1/3 the Tie-Sapphire cycle. But I would say that the theory is not as refined at all as with for the regular, phase matching partially ionized.
And that was done in a fiber cell?
It was done in fiber cell, and what we see is if there isn't some kind of structure there, there's also nonlinear effects happening. We can sort of see that there's a filamentation process happening also, and not surprising because we have to use a very, very high intensity. Because I lambda squared, if lambda is small, I has to be 10 times higher than Tie-Sapphire for the same energy. So not surprisingly, and because of the multiply ionized plasma, you do see some filamentation, and not surprisingly also, if there's some kind of structure around the beam, it enhances that filamentation. Again, this is not super surprising for those of us who've done filamentation either on purpose or by accident multiple times. But so the geometry matters, but in a different way. You don't need very high pressures because the single atom yield is so high. So we use 400 torr, less than an atmosphere. But we did find it doesn't work quite as well in just a cell or a gas jet. And again, just because we need help from nonlinear. Maybe if we had a more powerful laser, that would not be true. But because a plasma tends to defocus the beam, so that's what we might be getting help by some notching conditions.
Yeah.
I don't think I quite understand